Hi, this is Physics 1, Chapter 5, Circular Motion. And what we're going to do is talking about circular motion is we're going to start looking at objects moving around in a circle and changing direction, and what this means in terms of force, and what this means in terms of motions like speed, velocity, acceleration, stuff like that. So if we have an object starting to go around in a circle, or my mouse isn't, oh, I gotta plug this in. And it doesn't want to move. There we go. Let me make sure it writes here. Okay, looks like it's finding just fine. Alright, so when an object's going around in a circle, we're going to look at what's called the radius of curvature. Now, we don't need this object to make a complete circle. Okay, just a bend is enough to start to use this kind of approach to the forces, because we'll look at specific points around that bend basically, and all we're basically doing is breaking this then up into a line segment that's going around a circle. Okay, so just think every bend has a radius of curvature. It just maybe doesn't extend the whole way. And so when you have a changing direction, you have an acceleration. And this acceleration points towards the center of that circle. Okay, so acceleration is towards the center. Okay, and we actually call this a radial acceleration. And so we know the acceleration is equal to the velocity at a second point minus the velocity at a first point over some change in time. Okay, so we're looking at some change in velocity over change in time. And so what we're going to do is look at what's called similar triangles to show the formula for acceleration. Right, so we have 2 points here. Okay, so objects going from A to B. I'm going to kind of redraw this so I can draw on it. Actually, hold on a second. Maybe I would just copy that. Let me see if I can copy this. That'll work. Okay. So 2 points, object at A, object at B. All right, they're going around a bend, so each point they are same distance away from the center, or distance away. And so it's creating this kind of triangle here where you have the angle between C, the angle at A from this dotted line here, and the angle at B. And then you also have a vector, and this vector is horizontal, or you should say tangent to that curve, meaning it only touches this curve at A. So it's horizontal here, and as you go around the bend, it stays tangent to the circle. You know it's tangent because this angle here, not to that dotted line, but to that green line, is 9 degrees. And same thing here, it's 9 degrees, right? And so the line CA, which is here to here, and V1 are perpendicular. The line CB and V2 are perpendicular. And so the angle ACB, which is this angle, and the angle between V1 and V2 are the same. So if we take this vector and we just move it to here, so it looks like that, this angle and this angle are the same. Well, we know this angle is the subtraction of V2 minus V1 based on vector subtraction, right? So since V is not changing, V1 equals V2, which equals V. Okay, and so the speed is not going to be changing itself, but this subtraction here still holds as part of this acceleration. All right, so now what we can look at is the fact that this change in V and this dashed line that's a delta L are similar because they're similar triangles. So delta V and delta L are similar. And then V is going to be similar to R. Okay, so either one of these V's is similar to this R. So V1 equals V2 equals V. So when I say V, I mean both V2 and V1. And they're the same. Not the addition, but each of them together. And then R is the same. So I guess you can just kind of call this V now because they're equal to that. And so these V's are basically proportional to R. So the ratio of delta V to V is proportional to the ratio of delta L to R. And you just need one of these. Right? And so we can solve this for delta V. Oops, I don't need a similar sign. Equal sign. So V over R delta L. Oh, come on. Okay. And then what we're going to do is we won't get this in terms of acceleration. So our acceleration is going to be delta V over delta T, which is going to be equal to V delta L over R over delta T, which is going to be equal to, since you have V and delta L over delta T is a V, you're going to have V squared. That's this and this, and then this V over R. It's going to be equal to your acceleration. Right? And so this is how we show that the acceleration for something moving in a circular motion ends up being V squared over R. And this is, of course, at a constant velocity. Right? So if you lengthen the radius, you're lengthening the denominator here. You're increasing the denominator here, which is going to cause your acceleration to decrease. Right? And so the longer the radius, the object changes direction less rapidly. It doesn't change as fast as it turns. the greater the speed, you're increasing the speed, you increase the acceleration, and you increase it by a square. And so the greater the speed, the faster the object changes direction. So if you really increase the speed, you can really get that acceleration to be really fast. Think about somebody trying to zigzag through something. They do it really fast. They got a greater acceleration. They can get through the zigzag a lot easier than somebody going a lot bit slower. At the same time, if you really increase the radius around the bends they have to go, they can they'll really go a lot slower as they go around. So they have to make sharp, quick turns to zigzag fast. And we can see circular motion found in things, not just race cars going around a track, but in corners, pendulums, things that don't always have a full circular motion. So how much of that circular motion does become important? And so we're going to kind of define that. And that is the idea of revolution. One revolution is equal to one complete circle. Right, so one time around the circle, and that'd be one revolution. So you have a distance there of circumference, that's 2 pi r. You have an angle there of 2 pi, or we can say 360 degrees. And so one revolution, equals 2 pi radians. And one revolution equals 360 degrees. Then we define some other things. The period, and we're going to label it with a t. This is the time needed to complete one revolution. Okay, so whatever the time it takes to get around the circle, that's your period. Frequency is kind of this idea in reverse. We label frequency with an F, and it's the number of revolution in 1 second. And so frequency is the reciprocal of the period. So F equals 1 over T, or T equals 1 over F. And so for one revolution, we have the distance, we have the time. And so we can say the velocity for one revolution is equal to V equals D over T, which equals 2 pi r, which is your distance, over your period T. Now, if we're not talking about one revolution, this D doesn't always become 2 pi r. It could be whatever the distance is. You would have to find that based on the arc length, basically. So S equals r theta. So if you know what theta is, and we can say, you know what, I'll make this D for this. Usually they write S, but D equals r theta, so that that goes in there. So if it's 2 pi, it's going to be 2 pi r. If it's pi going half a circle, it would be pi times r. Alright, so let's get to an example here. Oops, you know what? Hold on a second. I opened up the wrong file, so let me get the one without the answers. You'll be able to stop the video and just write that one down real quick, but this isn't it. Alright, there we go. Alright. Alright, so what is the magnitude of the acceleration of a speck of clay on the edge of a potter's wheel, turning at 45 revolutions per minute if the wheel's diameter is 35 centimeters? Right, and so we have 45 revolutions per minute. That means that it makes 45 circles or rotations around. So 45 revolutions per 1 minute. So it goes around 45 times in one whole minute. And so if we divide that by 45 revs per 60 minutes, we get 0.75 revolutions per second. And then we're told that the diameter is 35 centimeters, so 0.35 meters. And they want to know the magnitude of the acceleration. Right. So we're given the diameter. Sometimes it's really, you gotta be really careful. That's the diameter. So you want the radius. That's gonna be 1.175 meters. Okay, you just cut the diameter in half. And we want the acceleration. Well, A equals v squared over r. Right, so let's see. We are given here how many revolutions. So we are not given, hold on a second. Let me get to my page here. So we are not being given directly V, but we can find V, right? And so what we're going to want to do is we're going to want to take V, and we're going to want to equal it to how many, how far did this speck of clay travel? And so this is one circumference, and then we need 45 circumferences. So we'll want 45 times 2 pi times the radius. And then we're going to want this over the time, which we know is 60 seconds. I just realized I wrote minutes up here, seconds. All right, so we know 45 over 60 is 0.75 times 2 pi times the radius, which is 0.175. So then pull up the calculator. You get 0.82. 825. And this would be, the radius is in meters. This is in revolutions. We don't usually take that into the idea of units and seconds or meters per second. And then our acceleration, as we said, a equals v squared over r. So now we need a equals 0.2825 squared over the radius. So square this, divide by 0.175, and you get 3.88, so 3.9 meters per second squared. And so this is the acceleration of this speck of clay as it goes around the edge of the wheel. Now we want to know the frequency and the period for this speck of clay. So we can do this in a couple ways. We can do what we did up here. This actually, how many revolutions per 1 minute. When we broke it down into how many revolutions per 1 second, that's exactly what we need to find for the frequency. Okay, remember the period is the time for 1 revolution. The frequency is the number of revolutions per 1 second. So that's what we have here. How many revolutions per 1 second? We already have the frequency. So to get the period, we just flip that 1 over 0.75. And that will give you, since we flip it, seconds over revolution, so seconds. One divided by 0.75. You get 1.33 seconds. All right, so now that we have a new formula for our acceleration, we can look at how this affects the force. And so to have an acceleration, we have to have a force. In order to change an object's path, we need to have a force. So acceleration requires some kind of force. We know that this force is going to be directed inwards and towards the center. Okay, in this case, we know that this hand is kind of providing that force for this ball to go around. So that is something we need to kind of look at. And I just want to kind of specify the difference here. Normal gravity, gravitational force, gravity force, friction, air resistance, some either even applied force. Right, just name a few of these. These all have some kind of source. This is the a surface pushing up, or the gravity pulling down, or for these, the molecules resistance, or some object, being pushed, some push or pull. Okay? They all have a source. Centripetal isn't something that has a source in a sense. It's something that is a condition. So all these have a source, and all of these can lead to different conditions. I think I spelled that wrong. don't know, it just doesn't look right. Conditions. First one is F equals ma, where these forces have some net force that's causing acceleration. The next one is F equals 0. So these forces provide some net force that ends up being in equilibrium. And then this is the third condition. That's mv squared over r, where a is your v squared over r. So your a equals v squared over r. So these forces have to provide that condition for this to happen. So in this case, this is applied force by this person swinging the string, pulling this ball inwards, causing it to go around. Okay, so there has to be some kind of forces pushing or causing this condition for this to happen. So centripetal force isn't one of these forces, but it's one of these conditions. And basically, what you're looking for at this point is you're looking for either acceleration here, equilibrium here, or circular motion here. And that's how you know which ones to use and when. All right, so let's get to an example. You have a bucket of mass 2. Oops, come on, the other way. No, I swear computers just try to force you to do things that you don't want to do. All right, so you have a mass that's 2 kilograms. You're pulling this in a vertical circle of radius 1.2 meters. At the lowest point of its motion, the tension in the rope supporting the bucket is 25 newtons. We want to find the speed of the bucket. Okay, so this is the lowest point. So let me do it this way. You have the rope, bucket's going around. So you have the bucket here. And it's tied to the rope. And you get a tension here of 25 newtons. Now, let's look at a free body diagram of this before we write in the tension. The weight obviously is going to be pulling down because it always pulls down. So that's mg pulling down. The tension is going to be pulling up for this bucket. It's going to be pulling towards that center. And so this ends up being your tension. Okay. For one, it has to be pulling towards the circle because there has to be something that's pulling this towards the circle. And so we can look at these two. We know that the centripetal force has to be towards the circle. So we have two forces, tension minus mg, and let's say up is positive, down is negative, has to equal mv squared over r. And then we want to find the speed. So we're going to solve this for v. So r times tension minus mg equals mv squared. So v equals square root of r times t minus mg over m. Now we can plug in the values. Square root, r is 1.2 meters, t is 25, m is 2, g is 9.8. erase that other parenthesis that I like. Okay. And then all this over 2. So let's type this in. It's 25 minus 19.6. That's 2 times 9.8 times 1.2. Divide that by 2. I get 3.24, and then take the square root. And get 1.8. So your velocity here is going to be 1.8. That provides 25 newtons back towards this, and we'll get it to go around in a circle. Alright. So now the next question. How fast must the bucket move at the top of the circle so that the rope does not go slack? Okay, this means that you're looking at the minimum speed for this bucket to be at the top, where this rope will stay just tight enough to keep it going around in a circle. Right, now let's look at this diagram and how we would set it up. And I'll keep the picture. I'm going to erase this stuff here. Right. So now if you're at the top here, you still got weight down. That'd be mg. You also have tension down. So you have two things going down. So what we're going to do, actually, you know what? I'll just make this negative, up is positive. You have negative mg minus t equals mv squared over r. Actually, no, it'd be easier just to make it positive now. We're doing a new section problem, I guess you can say, so we can switch this. This way, tension, any force this is going to be positive. Otherwise, we would have to make this negative, since this is going down as well, and then all these negatives cancel out. So we end up with positives either way. Okay, so positive, positive, and positive. All right. So now we gotta solve for v squared again, because it's still asking for velocity. So r times mg plus t over m equals v squared. So v equals square root of r times mg plus t over m. Okay, so if you want the minimum slack here, this means you can look at the right there at the border of when t equals 0. Right. The other way would be if t equals a negative number, which would be completely slacked and all that. So the borderline would be t equals 0. And so this just reduces down to v equals square root of r times mg over m, which actually reduces down to square root of r times g, which really makes it nice. You don't even have to worry about the mass. Right, so square root of 1.2 times 9.8. .43. Meters per second. All right, let me check the time. Okay. All right, so the next thing we're going to get into, and I'm going to do this in the next video, is curves. We're going to look at unbanked curves, and we're going to look at banked curves. And we're going to do a new way of solving these with the curves, because when we look at bank curves, it's not going to be solved the same way we did when we just look at a ramp. And there's a reason why. And it has to do again with centripetal force and the direction it's at. So we're going to be getting into that. And then let's see what else. We'll be doing Newton's law of universal gravity, which I'll show you why we use 9.8 for gravity. And I don't know if we'll do in 1 or 2 videos after this, but we'll see. Alright, I'll see you in the next video.